Okay, so today and for the next lecture, so we're going to start talking, this is over in chapter 9, nonlinear pharmacokinetics. And the model we're going to use is going to look pretty much like our regular one compartment model with an IV bolus dose, but on the elimination side, instead of KDL, we're going to have Km times C over Vmax plus C. I wrote that wrong. That's wrong. My elimination is not like that. I know something. Vmax times C. Vmax times C over Km plus C. That's what I want to do. So this is the model we're going to be talking about to explain nonlinear pharmacokinetics. Nonlinear pharmacokinetics also is referred to, you'll hear me saying dose-dependent pharmacokinetics sometimes also. They mean the same thing, dose-dependent. Dose-dependent pharmacokinetics. Again, this is in chapter 9. The title of that chapter is nonlinear. But if you hear me say dose-dependent pharmacokinetics, don't get bent out of shape. Now, it's called nonlinear or dose-dependent because all of the models we've talked about up to this point, the one compartment model with IV bolus dose, the one compartment model with absorption, the multiple dosing models, the two compartment models, all of those models were what we refer to as linear pharmacokinetic models, which means basically there are different ways to explain linearity. But there's proportionality between the dose and the concentration in all the other models we talked about. So we double the dose. If you look at all of those equations, you see if you double the dose, you double the concentration. So sidebar, for the one compartment model IV bolus dose, we had an equation that says that C is equal to dose over V times e to the power negative KL times T. You can see that there's proportionality. This is a linear model, the one compartment model IV bolus dose. There's proportionality between the dose and the concentration. So if nothing else changes, if I double the dose, the concentration is going to change. We don't have, and the same thing is true if you look at the equations for absorption, or if you look at the two compartment model. If we double the dose, the concentration will double. If we decrease the dose by 25%, the concentration comes down by 25%. That's one of the foundations of drug therapy. You know, if a physician is treating an illness and the concentration is not quite in the therapeutic range and it's like 10% below the therapeutic range or the therapeutic concentration, really all we need to do is increase the dose by 10% and that's going to kick it up 10%. Or the drug is showing toxic side effects and the concentration is 40% too high. It's 40% above the minimum toxic concentration. Then in theory, I could just reduce the dose by 40%. That would bring it back down to the therapeutic range. So there's proportionality for those situations where we have linear or first order pharmacokinetics, okay, like this situation. That's not true over here. With nonlinear pharmacokinetics, we don't have that kind of linearity or proportional effect, okay? So one of the common examples of a drug that shows dose-dependent pharmacokinetics is phenitoin. You know, that's a typical example. So if a patient is on phenitoin, okay, and that patient's concentration, if I want to bring that patient's concentration down from 15 milligrams per liter to 10 milligrams per liter, to go from 15 down to 10, okay, that's a not quite a 50% decrease, but let me make it simple. Let's say if I wanted to go from 12 milligrams per liter down to 6 milligrams per liter, steady state for a patient on phenitoin. That's a 50% decrease, right? We can do that in the head, from 12 to 6. That's a 50% decrease, right? Well, for phenitoin, we can't just decrease the dose by 50%. There's not proportionality between the concentration and the dose anymore for a drug that shows dose-dependent pharmacokinetics. So we need another means of adjusting the dose. Okay. We can't adjust it just based on the equation that looks like this or whatever. And we're going to learn about that. Hopefully we'll have time today. So with dose-dependent pharmacokinetics, those pharmacokinetic parameters that we talked about, like volume of distribution, clearance, elimination rate constants, they're not constant. They change with the dose. Remember, up to this point, we changed the dose for our first-order pharmacokinetic models, our so-called linear kinetic models. Okay, if we change the dose, the half-life didn't change. If we change the dose for a drug that shows linear pharmacokinetics, the volume of distribution didn't change. It was still the same volume of distribution. If we change the dose for a drug that shows linear pharmacokinetics, the clearance didn't change. Okay, but for these compounds that we're going to be talking about for this model, okay, either one or more of those pharmacokinetic parameters could change. If we change the dose, the half-life could change. If we change the dose, the volume of distribution may change. Not necessarily, but something's going to change, okay, as we change the dose. I mentioned phenetone. There are some other examples listed in your textbook. Probenecid is another example of a drug that shows dose-dependent pharmacokinetics. But there's a table, I said chapter 9, this is actually in chapter 10. This information is presented in chapter 10. Chapter 10, not chapter 9.
Good to you.
Chapter 10.
Sorry, thank you.
So there's a table, let me see if I can find it right quick. In that chapter. Oh, it's right on the second page of the chapter, on page 230, table 10.1. See table 10.1. Okay, in the textbook. They list some drugs that show dose-dependent pharmacokinetics. I don't need you to memorize that table. I want you to familiarize yourself with the table. Okay? And those drugs in the table. There are 3 common mechanisms. In that table, they have more than 3, okay? But there are 3 common mechanisms, as long as you can calculate half-life. That's my only calculate half-life. There are three common causes for a drug to show nonlinear pharmacokinetics, okay? Those 3 common causes are, usually we're gonna have saturation of something. Okay. Where's my markers going? Let me see. I got it there. We're gonna either have saturation of drug binding, okay, like binding of drugs in the plasma to protein, like a binding of drug to albumin. If that process becomes saturated, then that can lead to dose-dependent pharmacokinetics. So this is one of the common causes. Another common cause is saturation of drug transport. Remember earlier in the semester we talked about like passive diffusion and active transport. So passive processes don't become saturated. But those processes that proceed by facilitated diffusion and active transport, they can become saturated. Okay? And if one of those processes becomes saturated, like an active, like say for instance probenecid. Probenecid is actively transported from the plasma, okay, and secreted into the proximal tubule of the kidney. Okay, probenecid. You may have talked about probenecid in some of the other classes. If that carrier-mediated process, that drug transport process, if it becomes saturated, then probenecid will begin to show dose-dependent pharmacokinetics. Because you only got a limited number of those carriers that can move the drug from the plasma and secrete it into the proximal tubule. So if those carriers that's responsible for transporting the drug become saturated, then that drug is going to show dose-dependent pharmacokinetics. So that's one of the reasons why probenecid, and I think probenecid is listed in the table I asked you to study. Probenecid is in that table. And then a third reason is if we have saturation of enzyme processes. So saturation of enzymatic enzymatic processes, i.e., drug metabolism. That's probably the most common enzymatic process. Drug metabolism. Okay. So if drug metabolism becomes saturated, because you only got a certain amount of metabolic enzyme. In the case where we're talking about first order or linear pharmacokinetics, we got so much enzyme that the therapeutic concentration of the drug is so low. When we talk about first order pharmacokinetics, like with an IV bolus dose described by this equation, the drug concentration is so low relative to the enzymes that nothing is nowhere near saturation. Okay. But for some drugs like phenytoin, with phenytoin, the therapeutic concentration is high enough, the therapeutic concentration, the concentration that we need, the concentration that we need to achieve in order to keep the patient from convulsing and having seizures, is high enough that we begin to saturate the metabolism of phenytoin. So therefore, phenytoin shows dose-dependent or nonlinear pharmacokinetics. So I mentioned phenytoin, I mentioned probenecid. There's some other ones in this table here, but one of the common ones that I forgot to mention, and I don't know if it's in the table, is a drug that I won't say all of us, but most of us have come to know and love, and that is ethanol.
What?
Ethanol. Ethanol is a drug, okay? And ethanol, by that oxidative metabolism process that you may have talked about in biochemistry or some other course, ethanol, okay, shows dose-dependent pharmacokinetics. If you drink enough ethanol to become intoxicated. Okay, all of this stuff about dose-dependent pharmacokinetics is fine and dandy, but all of these drugs and compounds that show dose-dependent pharmacokinetics, they would just show regular first-order kinetics if the concentration is low enough. And we're going to talk more about that later. But it just so happened that the therapeutic concentration is high enough that we begin to saturate substances. So they get knocked over into that dose-dependent region. Most of the drugs that are prescribed and dispensed in the pharmacy could potentially show dose-dependent pharmacokinetics, but most of the drugs that you're going to be dispensing, the therapeutic concentration is low enough that we're not saturating anything, one of these processes, for most drugs. But there's some drugs like phenytoin where we get in the saturation region. Okay? The therapeutic concentration is high enough that we do begin to saturate one or more of these processes, and then the drug moves out of the first order region into the so-called dose-dependent region. Okay? Questions so far? Yes.
What's the therapeutic range for ethanol again?
Oh, I don't know if ethanol has a therapeutic range, but the point, if you just drink a thimble, if you ask me that, I might say, I could drink a gallon. You ask a Cherokee Indian, they might say, hey, the therapeutic range, is. But if you just drink a thimbleful of ethanol, most folks are not going to be intoxicated. That ethanol is just going to be eliminated by regular first order processes. But if you drink enough that to the point where you become inebriated, intoxicated, or slightly intoxicated, the elimination is not going to be first order anymore. It's going to be in this dose-dependent or nonlinear region. As concentration goes down, it will revert back to first order. So we're talking a little bit more about that also.
So there's a fluctuation between.
It can go back and forth between first order and zero order or nonlinear. And I hope I have time to show you how that works today. So basically, the kinetics associated for this simple model where we have an IV bolus dose, one compartment model, we're going to use the Michaelis-Menten equation to describe the elimination. You probably have seen this Vmax times C of Km plus C, and I'm associating that with Michaelis-Menten. You've heard of Michaelis-Menten kinetics before, right? Binding or whatever in biochemistry. You should have talked about Michaelis-Menten. It's only a couple of folks saying yeah, because I know students ain't gonna never acknowledge that they've learned something before because they want you to teach them all over again. Okay? That's the game now. Okay, I realize that. But I know in pre-pharmacy and in pharmacy school, you should have been introduced to Michaelis-Menten kinetics. So this is gonna be a big review. We're gonna use Michaelis-Menten kinetics to describe the elimination of drugs that show dose-dependent pharmacokinetics. So the Michaelis-Menten equation says that the change in drug concentration change in drug concentration is equal to V max times C over Km plus C. So this is the so-called Michaelis-Menten equation that you've seen before, where I got a negative sign here. I put the negative sign on this side, and then this is the positive on this side, but to me, it makes more sense on this side. You put it on each side you want to, okay? But when I put it here, it indicates that this concentration, this is the change in concentration over the change in time. It indicates that this concentration is going down. So we know that from our previous discussion with one of our model. If we give an IV bolus dose, you know, we get an initial concentration and then it starts heading downward. So that negative sign indicates that the concentration is going down. Okay. So this is the rate equation for this model, the so-called Michaelis-Menten equation. Michaelis-Menten. Michaelis-Menten, M-E-N-T-E-N. I think that's what you spell it. I don't take off the spelling here, but I'm just reminding you, okay, Michaelis, so this is the Michaelis-Menten equation. I don't know if Michaelis-Menten was one person or if it was two different people. That might have been a marriage name or something, I don't know, but it's been out for a long time. Okay, Vmax, this is a rate equation. Vmax is just the maximum rate. In this case, if we're talking about drug elimination, Vmax would be the maximum rate of drug elimination. So it's the maximum rate that the process can occur. It doesn't have to be eliminated. It could be the maximum rate of drug transport or the maximum rate of drug metabolism or whatever. But it's whatever the maximum is that's associated with whatever process we're talking about. Okay, whether it's binding or transport or enzymatic process. By the way, in that table 1, I mentioned this for those who came in late, but for those who were already here, just focus on those drugs primarily that one of these 3 because in that table, it's like 5 or 6 different mechanisms that can lead to dose-dependent pharmacokinetics. They got like 5 or 6 different categories. Just focus on the ones that fall under one of these 3 categories. Does that make sense? Like with phenotone, it's under, in that table, I think it says drug metabolism or something like that. Metabolism, so under metabolism, I see phenotone, for instance, because the reason phenotone shows dose-dependent pharmacokinetics is because saturation becomes metabolized, okay? So again, just familiarize yourself with the table and those drugs. I don't need you to memorize everything in the table, okay? Because I know you got a lot of other things going on. So Vmax is just the maximum rate. If we're talking about phenotone, it would be the maximum rate of phenotone metabolism. Does that make sense? It would be the maximum rate that phenotone can be metabolism. Phenotone can't be metabolized so fast because only a limited amount of those metabolic enzymes in the liver. Okay. So after you swamp those enzymes, i.e. after you saturate those enzymes, phenotone is going to keep on being metabolized. When I was in pharmacy school and I was taking kinetics and they talked about saturation, I thought saturation meant that the process shuts down. Now the process keeps going, but it's just going at its maximum speed. Until, you know, the enzymes regenerate, okay, they're not used up. So once I free up enough enzyme, again, because remember the concentration is steady going down. Okay. So once I get to the point where I don't have such a high concentration of drug anymore, those enzymes won't be saturated anymore, okay? And then I'll slowly revert back to an unsaturated situation. But as long as that concentration is real high relative to that fixed concentration of enzymes, okay, then I have a saturation process occurring, and that drug is going to continue to show dose-dependent pharmacokinetics. But the metabolic process, and we're talking about phenotone, it's saturated or not, that process is still occurring. It's just occurring at its maximum speed when we saturate it, okay? Km, C is the concentration. In this case, this C is this C right here, okay? In the Michaelis-Menten equation, that's the plasma concentration of the drug. Km is the so-called Michaelis-Menten constant. You've heard of that before. If you don't know anything else about that McKellar-Benton constant, please do know that it is a concentration. How do you know it's a concentration? Because look at the equation. I can add C to it. The only way we can add and subtract anything is that they have to have the same units. We can multiply apples times oranges. I said oranges, that's what I just said. We can multiply, no, I'm from the South, okay? We can multiply apples times oranges. You know, that's how we get these, you know, in math, that's how we get these funny units, like milligrams per minute. We can divide milligrams by minute, and we come up with something milligrams per minute, you know. We can multiply and divide unlike things, but we cannot add and subtract unlike things. So, if you didn't know before, please recognize that Km it has to have concentration units because this McKellar-Benton equation says I can add Km to C. Look at the numerator. V max and C got totally different units, but we can multiply those together and we just, you know, whatever the units are, what they are. So we can multiply and divide different things with different units, but we can't add and subtract. If something has different, you can't add and subtract. We gotta add apples to apples and oranges to oranges. We can't add apples to pecans. Well, I mean, we could do it, but mathematically speaking, you know, the units ain't gonna work out right, right? Now, the McKellar-Benton equation, this is important too, because, you know, if you open up the package insert, you know, for vinyl or package of phenotone, it'll have some information in there. One piece of information it's gonna have is the Km, the average Km value and the average Vmax value for phenotone. They put that in the packaging so the physician, if they need to adjust the dose or modify the dose, they can do it. We're gonna learn how to adjust the dose too based on Vmax and Km. So if we're talking about a drug that shows dose-dependent pharmacokinetics, you've seen this type of illustration before. If we look at the speed, delta C, the rate, delta C over delta T, versus concentration, this is a linear plot based on this equation right here. I don't want to say a linear plot. I want to say linear graph paper because what I'm going to show you is not going to be a straight line. Anybody remember how that's going to look? What's that going to look like if we look at rate versus concentration? Can anybody remember what that graph looks like on rectilinear paper? Anybody? I know you've seen it. I already know you've seen it before. I could probably talk about a Chivachar. I could probably talk to whoever you took in pre-pharmacy or whatever. Okay. Because they still talking about McKellar-Benton. Okay, it goes up and it plateaus off like that. That's okay. I'm just trying to see if you remember, but if you don't remember, you're gonna have to know it again now, okay? And this value up here, if I ran this all the way back to the y-axis, that's the value for Vmax. That's the maximum rate. Because delta C over delta T is just the rate. Vmax is just the maximum rate. Okay. So where that thing plateaus at is Vmax. A lot of times you see Vmax actually written over here on the graph itself, okay? Yes. But it's that y coordinate, okay? It's Vmax. So if I keep on increasing concentration, is that thing gonna go any faster? It can't go no faster. It can't go any faster. So I got control over drug concentration. I can keep on putting more and more drug in the body, or in the test tube, or in the beak. I can increase the concentration, but that rate is not going to go any faster, so-called Vmax. Okay. So see the relationship between the rate and Vmax. Vmax is just the maximum value that I can get with delta C over delta T. Vmax is going to have units of concentration over time. Well, let me not say that, okay? Let's just say that the units for the right side of this equation, for the whole right side of the equation, is going to be concentration over time. How do I know that? Because the units on the left side of the equation are concentration over time. So when I do all of the math for the right side of the equation, as the McKellar-Benton equation is written right now, all of this will come out with units of concentration over time. Let me see what else I want to say here. Oh, you probably learned also that Km from this graph, we're not going to be doing any analysis with this graph. We're going to take this equation and and I'm gonna linearize it. We're gonna linearize, we're gonna put it in the form of y equals mx plus d, so we can estimate Vmax and Km. But on this data, okay, if I come down to half of Vmax, and you've seen this before too, somewhere. So let's just say this is 0.5 times Vmax, half of Vmax, 0.5 Vmax. On a linear y-axis, linear scale, okay? Then if I go over to here, and I drop a vertical straight down, what's that value on the x-axis right there? See how good your memory is. On the x-axis. What's that? Huh? If I come down to half of Vmax, 0.5 Vmax, draw a horizontal line to my curve and drop a vertical straight down, that value now here is Km, sports fans. That's my Km value. So Km is defined as the concentration that will make this reaction or this process go at 1/2 of maximum. So whatever we already see that the speed is changing based on the concentration, right? The speed, when the concentration over here, I hope you see that the speed is lower, because if I take a concentration over here and go straight up to my line, the speed, delta C over delta T, is lower than when I'm over here. I hope you can see that over here, at a higher concentration, the speed is higher up on the graph. So the lower the concentration, the lower the speed. Some people are looking at me like, what the hell is he talking about? I want you to look at the graph and see that. That if delta C over delta T is the speed, the lower the concentration is, the lower the speed. The higher the concentration, the higher the speed. That's what this graph is showing. But I'm gonna get to a certain concentration where the speed ain't gonna go no faster. No faster. You can take Feld out of the country, but you can't take the country out of Feld. It's cool weather is just bringing it all out. Okay. Please see though that as I increase the concentration, that the speed is getting faster. Let's relate that to what's happening in the body. If I give a low dose of phenotone, it's going to be metabolized more slowly than if I give a high dose of phenotone. Talking about the speed of metabolism now. Delta C over delta T, the change in concentration. Because the drug metabolizes, the concentration is going to be changing. So a low dose of phenotone, okay, is going to be associated with a low rate of metabolism, a low delta C over delta T, a high dose, because now I have a higher concentration, okay? If I have a high concentration of something, doesn't that mean that as it goes through the liver, or whatever the metabolizing organ is, because there's so many more molecules floating around at a high concentration, then I'm getting more of those molecules metabolized per unit time? Because I got more molecules that's bombarding the enzyme. Whereas a low concentration, I just got a few molecules, so they don't interact with the enzyme directly. I forgot what you call that theory in chemistry or whatever. But the more molecules you have, the greater the chance of an interaction. So you're going to get a faster rate of metabolism at a high concentration versus what you would at a low concentration. So that's what this basically is suggesting in terms of drugs in the body. High concentrations, high rates, low concentration, low rates. But if I keep increasing the concentration, I'm gonna get to a rate where it ain't gonna increase anymore. That highest rate that can occur is so-called Vmax, the maximum velocity. Yes, ma'am.
Maybe please one more time give the Km definition.
It's the concentration. God, I was late. It's the concentration that will make whatever process we're looking at, whether it's drug transport, enzymatic processes, or whatever, or reaction. It's the concentration that would drive it at 1/2 of its maximum speed. That's what I'm trying to show you on this graph. That's why I came down from Vmax to half of Vmax. When I come to half of Vmax and I say, okay, what's the corresponding concentration? Well, then I got to look at what the concentration is. So I'll have to draw a line over. I'm going horizontally because horizontal is concentration. So that concentration down here on the x-axis is what Km is.
So we cannot say is concentration is half, it's just a speed is half.
Okay, I'm I'm gonna say it one more time and then you can see me after class. We've already established. See, what's happening in here is probably happening in other classes too. We've already established that Km is a concentration. We established that from the beginning. That is a concentration. Now I further defined it. It's the concentration which will make the velocity or the speed go at half of its maximum. Km is a concentration, but we already see that as concentration changes, the speed is changing based on this equation and based on this graphic. The speed over here, the velocity over here is higher than the concentration down here. Okay, I need you to see those relationships. If you just try to memorize this, then again, you set yourself up. Okay, so that's the equation. I got a few minutes, so because I want to have lab and I need you to work on some stuff, I know you're going to start studying for your exam, but right after your exam, you need to start on a laboratory assignment if you don't start before then. So I'm going to have to present this material in a little bit different order than I usually present it so that you can have something to do. So this is some background information. I'm going to give you some clinically relevant equations. We're going to derive them. And then next week I'll come back with the continuation of the background information, you know, with the McKellis-Menten equation. Okay. So, any questions about this so far? We're okay. Vmax, Km, I hope you can see the relationship between this graph. In other words, if we took concentration and we assumed the value for Vmax and Km and we plotted it in those rectilinear paper, it would go up and curve off like this, okay, based on this equation. This equation is not in linear form. But I just want you to see, like you've seen in some other classes, what happens here in this situation. So, in order to appropriately adjust the dose for a patient that's on a drug that shows dose-dependent pharmacokinetics, if we need to adjust the dose, then we need to have an estimation for Vmax and Km. Okay? So let's talk quickly about the determination of Vmax and Km. Clinical determination of Vmax and Km. Vmax and Km. Okay. I'm going to erase the graph part. I'm going to leave McKellis-Menten equation up there. Okay. So, normally, drugs that show dose-dependent pharmacokinetics, when we're dosing them, let's just assume we're going to be giving multiple dosing. You know, if a patient comes in with a seizure disorder and the doctor prescribes, the physician prescribes phenytoin, it ain't going to be just a single dose. They're going to be on that drug repetitively. They're going to be taking phenytoin, you know, once every 8 hours or whatever the dosing schedule is for phenytoin. Does that make sense? We ain't gonna be able to control the seizure by just giving the patient one dose and say, okay, you're good for the rest of your lifetime. So usually we're gonna be talking about multiple dosing, and with multiple dosing, we're gonna want to dose to steady state. Okay. So if we dose to steady state, if we dose all the way to steady state, okay, then remember at steady state, the rate that the drug is coming in, this is multiple dosing. This is multiple dosing, okay, not just a single dose, but this is the model we're using. Remember at steady state, the rate that the drug is being presented to the body is equal to the rate that the drug is being eliminated. So at steady state, at steady state, we don't need this negative sign because presumably at steady state, we'll reach a steady state concentration. This negative sign indicates, well, we need a single dose or whatever, yeah, and the concentration is going down. But at steady state, the concentration ain't gonna be going down. Does that make sense what I'm saying? At steady state. And we talked about two steady state models, so y'all don't look at me like, what the hell are you talking about? That concept is still the same. In steady state, we reach more or less a constant value for concentration. So the concentration is not going down, then that's just a positive sign there. If it's a positive sign, we don't need it. Okay. So at steady state, we got this situation going on, and we're gonna call this C steady state. I mean, two changes. We got rid of the negative sign, but I told you why, because we're at steady state. And it's still a plasma concentration, but it's a steady state concentration now. Can we funk with that? I did say funk again, that's what it is. Y'all fell in here, but then using profanity. Everybody in here know I don't curse. precept in practice. Okay, now another thing we want to do, another thing we want to do with this equation. I'm going to multiply both sides of this equation by a volume of distribution. So if I multiply this side of the equation by volume, and this is going to be amount over time, concentration over time now. If I multiply this side by volume distribution, it's going to be amount over time. And the amount over time, okay, I'm going to say multiplying by V. Multiplying through by the volume of distribution. Then on the left-hand side, this is going to be an amount over time. The amount over time that we're going to use in terms of the clinical dosing of the patient, we're going to call that amount over time the daily dose. If I'm taking 500 milligrams per day or something, wouldn't that be an amount over time? Okay. I'm going to call it a daily dose because when we get ready to calculate the dose for a patient, we calculate it as a daily dose. So, as an aside, let's say when we get through it all this, we calculate the daily dose as 1,000 milligrams. Okay, we're going to take that 1,000 milligrams per day and we're going to split it up the way that drug normally would be taken. So if it's a drug that's only taken once a day, then that patient will get the 1,000 milligrams in one dose, right? But if it's a drug that's taken 4 times a day, then that patient will get 250 milligrams 4 times a day, or QID. Does that make sense? If it's a drug that's taken twice a day, then if I solve for the daily dose, and the daily dose comes out to 1,000, but this is a drug that's taken twice a day, and we're going to get a patient 500 milligrams twice a day. Does that make sense? So don't get stuck on the daily dose. That's just a convenient way of expressing the amount over time once we multiply through by the volume of distribution. Okay. So I'm going to say the daily dose, which is an amount over time, okay, is equal to V max. With this V max right here, in the original equation, when I had concentration over time, this V max, okay, was expressed, the units for this V max would be concentration over time. In the original McKillis-Menten equation. In the original equation is concentration over time. If I multiply through by the volume of distribution, this V max is going to be amount over time. If it's concentration over time in this equation is concentration over time. But if I multiply this side by volume and this side by volume, if I multiply V max, concentration over time, times the volume, it's going to be an amount over time. So for right now, your textbook ain't going to explain it like this, and ain't going to show it like this. I'm going to call it V max prime, just temporarily, just to for you to keep in mind that this V max does not have the same value or units as this one up here. This one has been this V max prime is this one, which has been multiplied by a volume. If I multiply the V max by volume, then I don't need to do anything to C steady state. That's still going to be times C steady state, right? I've already, in other words, I don't need to multiply C steady state times volume too. The volume's already incorporated in here. Okay. And then that's going to be over. I don't need to do nothing to the denominator. Km plus C steady state. Talk to us for a second.
What would be the purpose of having a volume?
Cut the patient, cut the drug, and go into the body to distribute it. We're doing this because, don't forget what I'm trying to show you how in a clinical situation, we can calculate the Vmax and Km for a given patient. So we start out with the McKillis-Menten equation, and then we're doing sprinkling some powder. We okay so far? Yeah? No? I suppose so? This is an important relationship, so I'm gonna leave it here. I'm gonna leave it there. Yes, somebody had a question?
No, I was just trying to see that, the second part you wrote.
Okay.
Thank you.
Okay. So this Vmax now is gonna have units of amount over time. This one was concentration over time. This is amount over time. This is still concentration. This is still concentration. Okay. So one little thing we can do if we multiply both sides of the equation, if we cross multiply, I think that's what I want. I can say that daily dose times Km plus C steady state is equal to V max, I'm gonna still keep my prime time, times C steady state. If I multiply through these parentheses here, I can say that daily dose times Km plus daily dose times C steady state is equal to V max times C steady state. We together so far still? Daily dose divided by, and then if I subtract daily dose times Km from both sides, let me see if this is gonna work. Is equal to V max prime times C steady state minus, let me see if I subtracted the right thing. If I didn't, I'll go back and subtract the other one. There's only two choices here. Daily dose, bang, bang. I think I got lucky this time. Everybody, take a look, take a deep breath and look at this so far. Everybody see what I'm doing? I cross multiply, using this to get this one. Okay, so I'm just doing algebraic manipulation so far. Questions so far? I'm gonna show you an equation that's in the textbook, but they don't go through these steps. They just gonna give you the final equation. But because you're TSU's finalists, I'm trying to show you how you got there, okay? If you decide you wanna go to the book to look up some of this stuff. So if I divide both sides by C steady state now, then if I divide this, I'm gonna say divided by C steady state, dividing by C steady state, I get that daily dose is equal to, because if I divide this by C steady state, they're gonna cancel, right? So I don't want you to say, well, how do you do that? I'm telling you, you got to divide through by C steady state. On the right hand side of the equation, I'm gonna get V max prime, and if I divide V max prime times C steady state divided by C steady state, I'm just left with this right here, right? Okay. And then that's gonna be minus daily dose times Km divided by C steady state. Talk to me, sports fans. Talk to me.
How did the D's duplicate?
Talk to me, sports fans. Say what I said again.
How did the D's duplicate?
How did the D's duplicate?
She wants
The
to-
D, the two D's just mean daily dose.
Yeah, I know, but like, they're on each side of the equation. Oh, okay. Because it's a bit, it's like,
Daily dose times Km, daily dose times C steady state.
I'm saying on the third one.
I'm saying, see me after class. I will get to next year. I'm saying, see me after class.
Oh my gosh.
Janae. Okay. I'm saying, see. So, do you see how we go from here to here?
Yeah, I get that.
You get that? Well, if I subtract daily dose times Km from the left hand side, then it's gonna come over here on that side. I just subtracted. I got to carry it all together though because of the product. So I had to carry this whole thing. When I subtracted, I had to carry this whole thing from this side over to that side. Amen? I just thought you always doing something tricky. I just don't. Okay. All right. It's straight up algebra at this point. So this is an important relationship. Okay. Because we can write this as or daily dose is equal to daily dose times Km over C steady state minus V max. I'm gonna just keep the prime there, okay? So you see we go from here to here. Now this equation is in linear form, where if we do a plot of daily dose on the y-axis, remember what we're trying to do now, determine V max and Km. That's the whole idea behind this little transformation of Michaelis-Menten equation. And if we plot daily dose over C steady state on the x-axis, let me see how good your vision is. This is a rectilinear piece of graph paper. Linear x scale, linear y scale. You don't see the laws of exponents in my equation, right? Okay. So if I do a graph of daily dose, in other words, how much drug the patient is taking daily, over daily dose divided by C steady state. Let me see if I can bring that up so that I can see it. Yeah. This is important. I mean, it's all important, but this is the culmination of what we were talking about. So if I did a graph of the daily dose administered to the patient over daily dose divided by C steady state, we can get the C steady state, the results from each daily dose. Once we reach steady state, we just draw a blood sample and send it to the laboratory, and ask the laboratory to tell us what the concentration was at that particular daily dose, okay? What's that graph gonna look like based on this equation? Anybody? Somebody describe it to me right quick. Should it be a straight line? Should it have negative slope, positive slope? Anybody? Straight line, let me say it. Tell me about the slope and the intercept of that line.
It's positive.
What's positive? The intercept, the slope, or both, or what?
Both.
The slope is positive?
Mm-hmm.
Did I do that right?
Cause I'm gonna say, how come?
Wait a minute. Everybody see that I wrote this? Y'all let me get away with murder. And you see that this and this are not the same? Somebody pull my coattail. Because in this one I got a positive V max, and this one I got a negative V max. I did something wrong, and y'all just let me just keep right on going.
I thought maybe this is part of what you're teaching.
He
Don't
said
miss
or.
the thought. I mean,
He said or.
these two relationships are not equivalent here. So let me rewrite this. This should be
Negative slope.
Negative is slow and
plus. Okay, and this is negative in front of that.
And now we know it's gonna be a negative slope.
Okay, so now Linda, go ahead on.
It's negative is slow and positive.
In your textbook, by the way, they're gonna have V max coming first, and then they're gonna say minus, but it's the same thing. Yeah, it's the same thing. Okay, Linda, you were saying?
Now is negative is slow and positive, the prime.
Okay, what's the value of the slope gonna be according to the equation?
Daily dose or CS steady.
Okay, that's good enough for me. No, that's wrong. That's not right. I thought it was good. What's slope gonna be? She was almost right. Huh? The slope gonna be negative Km. So if I plot that data, okay, according to that equation right there, if I'm telling you that we're putting daily dose on the x-axis, and daily dose over C steady state on the x-axis, okay. Or daily dose is equal to V max, I can say prime, minus daily dose over C steady state times Km. Maybe you can see it better this way. So if I'm putting daily dose over C steady state on the x-axis, it's gonna have a negative slope associated with it. Y is equal to mxb, okay? So the slope of this line is gonna be equal to negative Km. The slope of the line is equal to negative Km. And this back extrapolated intercept right here is equal to V max. According to the equation. Okay? So I'm gonna stop right there. I see JD is setting up.
I was trying to get you in.
Okay. So what I want you to do in preparation, and I'll probably have to do a little bit of lecture in the laboratory, but I think you can at least get started. There is a worked example in the textbook that utilizes, one or both of these equations that I blocked off, this one and this one, okay? So take a look at that example. They work in 3 different ways. This is a worked example on page 238. Okay? And the method that they're using that I want you to focus on, the other ones you don't even have to worry about. In figure 10.10, figure 10.10, it's a worked example. They work by 3 different methods. We're only interested in one. The method that we're interested in is shown in figure 10.10, okay? Okay? So they, in figure 1010, they plot the daily dose, they call it R, and they plot that against daily dose divided by C steady state, which is the same thing as clearance. Look at figure 1010, work through that example. I want you to actually get a sheet of graph paper, graph the data, see if you can reproduce that graph that they have in figure 1010, you know, based on the example given on page 238. And then at the end of the chapter, there's some problems that I want you to start working on. At the end of the chapter, our focus for next week's laboratory will be question number 1, 2, 3, 4, 6, 7, 8, 9. I'll repeat those. 1, 2, 3, 4, 6, 7, 8, and 9. And 11. For good measure. For good measure. Okay? All right.